Yeah. So hello guys, welcome everyone to our webinar. Today we have Venus Keus. Venus got her PhD from the University of Liège in 2012. After that, she went to University of Southampton for a postdoc, and currently she is a postdoc at the University of Helsinki. Today she's gonna talk about the problem of hierarchy of fermion masses, Frogincent mechanism, dark matter. So it's a pleasure to have you here, Venus, with us. Please. Before we start, just an advertisement. For you guys, for the audience, you can make questions with the microphone if you want, or via chat. We can read your questions. So don't be shy. Ask for Venus. And please, Venus.
Yeah. Thank you very much. Yeah, thanks for having me. As I said, I've always wanted to visit Brazil. So I'm very glad to be giving a talk to your group. As Tessio said, please do interrupt me throughout the talk if you have any questions. I'd rather go slow and make sure everybody kind of understands what I'm talking about than zoom through and get it finished. So what I'm going to talk about is a well-motivated particle physics model which aims to kind of explain the fermion mass hierarchy. And it hasn't been thought of, or the model hasn't been put together as a dark matter model. But what we try to do here is to see if these two kind of problems of the standard model could have the same origin. Okay, so let me just talk about the agenda of the talk. I'll kind of give you a bit of motivation why we thought this would be an interesting direction to go. Then I'll tell you about this particle physics mechanism that I mentioned, the Frogincent mechanism that was put together in late 60s for kind of giving some sort of an explanation for the mass hierarchy. Which it does that by kind of obviously assuming extra particles on top of the standard model content. One of the kind of main particles that the Frogincent proposes is a scalar called flavon. This flavon kind of couples to the fermions, and depending on how it couples, you kind of get a different hierarchy between the fermions. Then I'll kind of switch gears completely, go away from particle physics, talk a little bit about cosmology and dark matter, and then I bring it together by trying to see if we went for a flavon, let's just say focusing on the charged leptonic sector, could we also explain or provide a viable dark matter candidate at the same time. So let's just start with a kind of happy slide that we all love the standard model. Its current formulation was basically finalized in the 70s. And since then, experiments have over and over again kind of reaffirmed the precision or the correctness of the standard model. So the W and Z gauge bosons were discovered in 83, the top quark was discovered in 95, the tau neutrino in 2000, and for the purpose of this talk, a Higgs boson was discovered in 2012. So we know the standard model is kind of describing nature very, very well, but we know that the standard model isn't the full theory of nature. However, at the best experiment that we have at the LHC, so far, all we see is consistent with the standard model, and no kind of significant deviation from the standard model has been observed, or any sign of new physics. But as I said, theoretically, we know that the standard model is not the complete theory of nature. So there are many reasons that we know we have to go beyond the standard model, but the two kind of shortcomings of the standard model that I'm going to focus on here are the fermion mass hierarchy and the dark matter abundance. So when you look at the particle content of the standard model, you see that the electron, the lightest charged lepton, has a mass about 6 orders of magnitude lighter than the top quark. And kind of the standard model claiming that all these masses are somehow described by the Higgs mechanism, you kind of have no reason why there should be such a big hierarchy between the masses. If you look at the neutrinos, the situation is even worse. With the, well, we don't know exactly what the mass of the neutrinos are, but we know roughly. And then the mass hierarchy is even larger. It's something about 10 to 15 orders of magnitude difference between the top quark and the neutrino masses. And as I said, the standard model gives you no explanation why. So these masses are just something that we measure experimentally and have no kind of natural way of producing them. On the cosmology side, we know that about 24 to 25% of the matter density of the universe is of something that we don't see. We call it dark matter, but none of the particles in the standard model have the characteristics that one expects from a dark matter candidate. So what I'm going to try to do is kind of use one framework that would solve these two problems. So starting with the particle physics, I'm going to briefly introduce the Frogincent mechanism. So this bit has a lot of equations, but I hope I don't lose you by the end of this section. I've added a lot of colors to kind of make it more happy looking. But yeah, let's see by the end of this section how many people are still awake. So as I mentioned, the Frogincent mechanism predicts these extra particles beyond the standard model. At the low energy, the particle content of the Frogincent is basically just one extra scalar on top of what the standard model has. So I don't know if you can see my cursor here or not, but basically in the scalar sector, you have the standard model Higgs doublet and this singlet, the scalar singlet, the flavon. So this guy transforms trivially under the standard model gauge group because it is a singlet. But there is this Frogincent U1 symmetry, let's say, under which all the standard model particles have a specific charge. So this phi is, by the way, a complex scalar with a real part and an imaginary part. At high energies, the Frogincent also assumes the existence of these heavy fermions that are kind of represented here by chi A and chi B. So when you write your Yukawa bit of the Lagrangian, you don't actually have the simple order 4 operator. Your Yukawa Lagrangian comes from a higher order operator, which has the flavon in it to some power, depending on how many flavons kind of coupled to your standard model fermions. And these heavy fermions, which we kind of integrate out, and the only trace that they leave at low energy is this scale of new physics, which is kind of proportional to their mass. So then your standard model Yukawa kind of interaction is written like this. Basically, then this would be the diagram that represents that that operator. And when you integrate out these heavy fermions, the chi A and chi B, what this operator looks like is a non-renormalizable operator, higher order operator of this type. So remember that there is this U1 Frogincent symmetry that is respected by your Lagrangian. So each vertex would have to be U1 symmetric. and that depends on the charges, the U1 charges that you've given your standard model fermions, your Higgs, and the flavon. And basically, how you distinguish between different fermions is by the number of flavons that kind of appear at this effective vertex. So you see, then after electroweak symmetry breaking, or after the flavon gets a VIV, this basically reduces to the Yukawa interaction that we know, with the Yukawa coupling being kind of proportional to the Cij, which are just order one coefficients that you put in front of the operator. And so, as I said, the flavon is now replaced by the VIV of the flavon, and there's this Nij, which depends on the number of flavons that go into this vertex. So
Excuse
then
me,
you
Venus.
sure. Yep.
I have a question about these fermions, these heavy
Yep.
fermions, because you say that in high energy they will appear, right?
Yeah.
But you just introduced a scalar, phi. How these fermions emerges in the model?
Oh, so maybe I shouldn't have said that it's a U1 kind of complete theory. Basically, all they want to say is that, yeah, there are these fermions, they have certain charges, but that's just to give an explanation for this higher order operator, basically. As you can see, they give no information about their masses. Their only contribution to the low energy is the scale of new physics.
Okay, so it's a kind of virtual particle.
Definitely, in low energy, it is a virtual particle, yeah. And they're so heavy, like above 10 TeV or so. And basically that, what do you call it, that scale is dependent on what the experimentalists find, right? We know already up to, let's say, a few TeV, there is no new physics. So nobody claims to have heavy fermions that are around 1 TeV. Of course, that depends on how these fermions couple to the standard model particles, but basically that's the only time you hear from these heavy fermions, just that they are integrated out. So the low energy theory that you work with, you never see these guys. Is that clear?
Yes, thank you.
Yeah, good, thank you. Okay, so let me now kind of show you a little bit more of these fun equations. So as I said, then every vertex that you write has to be U1 symmetric. This U1 is the Frogincent U1 symmetry, the extra symmetry that you've introduced. And at each vertex, the sum of the U1 charges has to be 0, or the term has to be invariant under the U1 symmetry. So basically, if you add the charges of all the particles that sit here, you will have to end up with 0. So here, the left-handed anti-fermion would have this charge. So that's the definition that we're giving. And what these charges are basically, you pick them. So it might not look as natural, because depending on what you want to predict with your Frogincent mechanism, of course, when they introduced it, the intention was to give a reasonable explanation of the hierarchy between the masses. And as I show you some examples, you will see that depending on what U1 charges you assign to your fermions, your Yukawa texture looks different. But basically, at a very generic level, the sum of the U1 charges have to be 0 for each vertex. So for this vertex, the QH, the U1 charge of the Higgs, the charges of the right-handed and left-handed fermions, and n times the charge that you've given to the flavon, because you're going to have more than one flavon depending on which fermion you're putting in this interaction. But at the end of the day, the sum of these charges has to go to 0. So for kind of, it's a simple choice if you pick the flavon charge to be -1 and the Higgs charge to be 0, because then you could kind of rewrite this Nij as basically this, and having set QH and Q phi to 0 and -1, what you end up with is just the charge of the left-handed fermion and the right-handed fermion. So let's go back to the higher order operator. After the electroweak symmetry breaking, you could replace the doublet with its particle, with the Higgs, and the flavon could be replaced by its Viv. And knowing that this is the scale of new physics, which is high, you could tell that this is a small quantity. This small quantity is usually represented by epsilon. So basically, these order 1 coefficients times this epsilon with a certain power is what is going to be your Yukawa coupling. So basically, what we do is that, I can't highlight it, but yeah, basically your Yij is going to be this order 1 coefficient, epsilon to the power of Nij. And Nij is then basically the sum of the charges of the left-handed and right-handed fermions. So let me give you an example so that it's a little bit clearer. As I mentioned in the beginning, we want to focus on a flavon that is responsible for explaining the charged lepton mass hierarchy. So in the charged lepton sector, we have electron, whose mass is about half MeV, the muon, whose mass is a good 100 times more, 2 orders of magnitude larger than the electron mass, and then the tau, which is again 1 order of magnitude larger than the muon mass. So that means the charges that you give to your standard model fermions would have to kind of come together in such a way that your Yukawa matrix actually gives the correct masses, or the correct observed masses for these charged leptons. Remembering that even though here, because this Yij is not a diagonal matrix anymore, so you do have off-diagonal elements, but at the end of the day, the diagonal elements are the ones that are kind of roughly proportional to the mass of the particle. So, for example, and the value of epsilon is kind of up to you. You could say, so it's vivified divided by the order of the scale of new physics, and you could say, okay, I take epsilon to be 0.1. In the original paper by Frogincent and Nielsen, it was taken to be 0.2, with which they describe the CKM matrix kind of texture. So here, again, let's say you could say my epsilon's 10 to -2. Then you know kind of roughly, so remember that you have these order 1 coefficients here, the Cij, that you could put in to kind of get exactly the correct masses for the leptons. But roughly, with an epsilon of 10 to -2, you see that the electron is, so it has 1 higher order of epsilon, meaning it's 2 orders of magnitude lighter or smaller than the muon, which is actually what you see in nature. Or between the tau and the muon, tau is about 1 order of magnitude, 2 orders of magnitude, let's say, heavier than the muon, and you see that there is 1 power of epsilon difference between the 3,3 element, which is going to be relevant for the tau lepton, and the 2,2 element, which corresponds to the muon. So kind of you can get a rough idea of what your epsilon powers should be, and then the off-diagonal elements are basically the sum of the charges of non-diagonal, or let's say Flavour violating bits. So here you have epsilon to the power of the left-handed electron plus the right-handed electron, which is 3, as you can see here. Then the second element is left-handed electron, right-handed muon, which is again epsilon to the power of 3. And the last term, the 1,3 term, is left-handed electron plus the right-handed tau, which is again 3. So the fact that these off-diagonal elements are kind of smaller than the diagonal elements also tells you that the flavor violating interactions are not dominant. So again, if you had gone for a different epsilon, let's say you've taken your epsilon to be 0.1, meaning that you assume the scale of new physics to be 10 times higher than the flavon wave, because the flavon wave is not something that you particularly choose. It's something that you kind of get constraints on from observation and experiment. Whereas the scale of new physics, let's say experimentally, we know that it's definitely above 1 TeV, but it's up to you to say where these heavy fermions are. What I'm saying is that basically for this low energy physics that we're doing, this doesn't really matter. What matters is that whatever value of epsilon you pick, make sure that you can kind of fix roughly the order of the masses of leptons with the charges that you give to your leptons, and then you fix exactly the correct masses or Yukawa couplings that come out by adjusting these order 1 coefficients. Remember the Cij that we're going to sit in front of these epsilons. So that's something like they call that the Yukawa texture. Okay. Now, let me go back to the messy equations and see where is this effect now?
Venus, I have a question. So in this mechanism, you managed to get all the Cij coefficients of order 1?
Yes.
They are not hierarchical.
No, actually, so that's the whole point, that you don't have to kind of, I'm very aware that this kind of feels very uncomfortable as a young physicist, but when you talk to more senior physicists, they all have their idea of what is natural, what is not natural. So if you come up with a new mechanism with a new symmetry under which the charges of your left-handed leptons are 6, 4, and 2, and the right-handed leptons have 0 charge, apparently nobody tells you that you're doing something unnatural, because in the standard model, the hypercharges are also random. We have 1/6, we have 2/3. How is that natural and this isn't? So again, it's kind of, it's an area I'd rather not get into. But the idea is that, yes, you kind of try to fix the kind of big scales, big scale differences, like the, whatever, like 3 orders of magnitude difference between the mass of the electron and the tau by fixing the powers of the epsilon. But then those teeny tiny kind of, we need to get the mass of the electron to be exactly 0.511 MeV, then you fix those with the order 1 coefficients. So, and when the order 1 coefficients are just basically moving between, I don't know, 0.1 to 0.9, then the consensus is that you don't have to give a justification. But you do need to give a justification for a 6 orders of magnitude mass difference. So it's a little bit of a dodgy area. You're not exactly giving a complete theory of everything, saying this is exactly the mass of the electron that comes out of my theory. But instead, you kind of translate the hierarchy in the masses to a hierarchy, if you wish, of the new symmetry charges that I give to fermions. So,
Okay.
Yeah.
Go ahead.
Yeah, thank you. Sorry, I thought there's another question.
Yeah, I have another question. So this U1 symmetry is global, right?
Yes, it is.
You know, if people try to gauge this symmetry, and maybe the anomaly cancellations can constrain these charges and see if it works.
So actually, if you gauge this U1 symmetry, then you're basically producing a Z prime, let's say. Then, depending on what you want to do with your Frogincent mechanism, because yeah, the very first time we actually wrote a paper on this was that we were trying to describe the Higgs to mu tau axis that was observed at the LHC. But with a gauged U1 symmetry and predicting an extra neutral boson, let's call it Z prime, there are so many constraints on the mass and the couplings of this this Z prime that you basically have to, as I'll show you later, assume that the VIV of this flavon is really, really large, because as you will see, the couplings are inversely proportional to the VIV of the flavon. So with a VIV that's of order 10 to 16 GeV, it's kind of uneasy to be having a VIV that is, at Planck scale. So I think the model already runs into such troubles as, can you explain why your flavon VIV is 10 to 16 GeV and the electroweak VIV is at 100 GeV? That, yeah, the anomaly cancellation is a whole other kind of can of worms to open. But yes, one would have to worry about anomaly cancellations, and that would put some sort of a constraint on the charges of the fermions.
So this is the typical value of the VIV of the flavon and to the
so as I said, in the original paper, they had taken epsilon to be 0.2. And what they were trying to do was using one flavon to describe the masses of the hierarchy of the masses of the quarks and the charged leptons, which is quite difficult. Because yeah, so in the quark sector you have a top which is 170 GeV, so still 2 orders of magnitude heavier than the top, and then you have an up-type quark which is about 1 MeV or so. So you have to kind of be quite generous with your order 1 coefficients, but the charges are usually order 1. Yeah, at least in all the papers that I've seen that use this mechanism, the charges of order 1 are of order 1, and the order 1 coefficients by definition are of order 1.
Okay, fine, thanks.
Good. Sure. Can I go forward?
Yes.
Yeah, okay. So back to the fun equations. Let me remind you again that your Yukawa bit of the Lagrangian now appears as a higher order operator. And yeah, so when you kind of, the electroweak symmetry is broken, and your Higgs doublet and your phi singlet have acquired their VIVs, you can kind of expand the Yukawa Lagrangian. What I've done here is that I've simply replaced H with VH plus H over square root of 2 and phi with V phi plus phi over square root of 2, and did a little expansion of kind of, if this is a very small ratio, I can bring Nij down here, and only kept, so there's also an order 5 term, which I haven't written here, which would be an H phi LL kind of a term. So as I mentioned before, here I'm trying to just look at the charged leptons. So I've replaced these F for fermions with L, and the reason they've got a prime is that I'm still in the gauge eigenbasis. So kind of having opened up these constructions, I've got my Yukawa interaction in the lepton gauge basis. Then you use these unitary matrices UL and UR to rotate the lepton gauge states into the leptonic mass basis, exactly the way you do in the standard model. And what these unitary matrices do is that they diagonalize the Yij matrix that sits in front of the Higgs interaction with the leptons, right? So they diagonalize the mass matrix and simultaneously the Yukawa matrix. So what you end up with is a diagonal mass matrix with LL, so the off-diagonal elements are 0. Same things The same thing happens for the interactions with the Higgs, but note that the bit with the flavon also has an Nij, which is a non-diagonal matrix in front of it. And obviously, you can't simultaneously diagonalize Yij and Yij times Nij, well, unless you really fine-tune your model. But in general, what you end up with for the interactions of the flavon and the leptons is some non-diagonal matrix, which I've called kappa ij, having pulled out this VH and V phi and a square root of 2, I basically call this whole thing kappa tilde ij. So your effective Yukawa Lagrangian now has a diagonal mass matrix, a diagonal interaction with the Higgs, and the non-diagonal interactions with phi. So again, I want to show you the, for the purpose of this project, these are the charges that we gave to our charged leptons. So we kind of, went with U1 charge 3 for electron, both the left-handed and right-handed component, 2 for the mu's, and 1 for the taus. And as I said before, for the flavon, we give the charge -1 and assume that Higgs doesn't transform or transforms trivially under this U1 symmetry. Then the Yukawa matrix that you would get, again, look at the diagonal elements, you see that there's kind of an order, 2 orders of magnitude difference, which roughly satisfies the order of the masses in the charged leptons. And yeah, so what is important is then this kappa tilde matrix, which you see again. So let me just remind you, the kappa tilde is this guy, right? So the diagonal elements come out to be quite close to the masses of the charged leptons, where the off-diagonal elements have some proportionality to epsilon, which kind of makes them smaller. And here, I've forgotten to write it out, but epsilon, we take it to be 0.1. You don't have to remember all of this. What you do need to remember is that this kappa tilde, which is the coupling of the flavon with the leptons, is inversely proportional to the wave of phi. So now kind of knowing roughly what the model looks like and what are our interaction strengths, we can go ahead and see what experiments have predictions or constraints for this model. So the reason you need to worry about experimental constraints is that when you look at your scalar potential, you see that on top of the standard model bits of the scalar potential, you now can easily write these terms for the flavon, right? These are renormalizable terms that your model allows, or the potential, or allowed in the potential, and you have to write them out with the usual portal coupling. And here we've kind of written this mass term or softly breaking term, which will be the source of the mass of this eta, because otherwise this would be a perfect U1 symmetry, which when you break, you'll end up with a massless pseudo-Goldstone boson, or Goldstone boson, in which case, this eta would be a massless particle. So instead of having introduced this soft breaking term, you will have the CP, or the real part, the CP even bit of the flavon mixing with the Higgs from the standard model Higgs doublet. So this mixing can be described or quantized by this angle sine theta, which you can easily write in terms of the parameters of the potential. And the two physical particles that come out of this mixture are H1 and H2. We take H1 to be the 125 GeV boson that's observed at the LHC, and we take H2 to be around 500 or so GeV. And it's a few hundreds of GeV, so kind of scale-wise, it's not that far away from the standard model Higgs. And what we've noticed is that the phenomenology of what is coming is not very dependent on the mass of this H2. So for the plots that I'll show you later, we take this H2 to be around 500 GeV. But as I mentioned, this eta, who's now a pseudo-Goldstone boson, whose mass is proportional to this softly breaking term, is a light particle. Naturally, a pseudo-Goldstone boson is a light particle. But we also want to see if this guy could play the role of dark matter. And if it is quite heavy, it could decay to this flavon by definition coupled to leptons. If it's too heavy, it could easily decay to, let's say, a pair of electrons. So theoretically, it's kind of understood that it's light, but also for the purpose of this project, you want it to be small as well. So small enough that it doesn't decay at tree level to any charged leptons. So it's definitely lighter than twice the mass of the electron. And then we want to see if there's anything that's kind of limiting us or putting a lower bound on the mass of this eta. Okay, so now having talked about these two states that mix with each other, you see that even though the kind of gauge eigenstate H didn't have any flavor changing charged lepton flavor violating processes or interactions, but through having mixed with phi, which does have charged lepton flavor violating or CLFV interactions, H also inherits some of these interactions. So the first thing you need to worry about is the experimental bounds on these charged lepton flavor violating processes. The experiments done on these processes are very, very precise, and the bounds that you get on your models are very, very constraining. The strongest constraint comes from what is known as the mu to E conversion or mu to E gamma process. There are also the kind of Li to Lj or 3Lj, what would you call it, conversion. But you see that the bound that they have on the branching ratio of these processes is not as constraining as the mu to E gamma branching ratio, which is 10 to minus 13. You also have the mu to E conversion, which kind of is a process that takes place near, let's say, a gold atom. And these bounds are kind of strong, but depending on your model, you will see that one of these processes is the one that's the most constraining. In the case of our Frogincent mechanism, the most constraining bound does indeed come from the mu to E gamma branching ratio, which has to be less than 10 to minus 13. So let me actually show you a couple of diagrams telling you what these processes are. So the Li decaying to 3 other leptons, that's a process of this type. So you see that at each vertex, you have a flavor or lepton flavor violating process. So obviously, by definition, if you don't have, if the flavon didn't mix with the Higgs at all, you would have zero contribution to this process from H1 and H2. Nonetheless, H1 and H2 have inherited CLFV couplings from the flavon, but because they are quite heavy, their contribution to these processes doesn't really matter. And as I mentioned, we want this eta to be light enough so it doesn't decay at tree level to, let's say, electrons. And you can see with a mass lighter than 1 MeV, this guy will take over, will dominate all of these processes. So in the, let's say, mu to triple E interaction, you do have 2 flavor violating vertices, which means that they are the off-diagonal elements. which means that they are kind of small-ish compared to the diagonal elements. In the mu to E conversion, again, you could have the process at loop level with the exchange of an eta. And yeah, then here you could assume, let's say this is also a muon, so you have no Flavour violating vertex, which would reduce the cross-section or the branching ratio of this process. Whereas here you would have a CLFV vertex. And there's a mu to E gamma process, which, as I said, is the most constraining one. And it's actually the muon in the loop that's kind of, that's the dominant one. So by in the loop, I mean here. Of course, the scalar that dominates this process is eta. So for the texture that we put together, so that this would be my texture. These would be my U1 charges. For this texture, the strongest bound on my model is from the mu to E process, which, so remember, we talked about the couplings being inversely proportional to the VEV of the flavon. So if I have a lower bound on the branching ratio of this process, it puts a lower bound on the value of the VEV of the flavon. Because if my flavon VEV is larger than this, then my interaction strength would be smaller, meaning that the branching ratio of the process would be smaller. So particle physics-wise, this is the most constraining bound we've got. And as long as eta is lighter than twice the mass of the electron, or much lighter than the muon, this bound doesn't really depend on the mass of the eta. So as you see later on, when we're looking at the dark matter properties of this eta, we keep on changing the mass of the eta to see what happens in different regions of the parameter space. But this bound has nothing to do with the mass of the eta. It just tells you there is a lower bound on the flavon VEV, which you have to respect. So as far as particle physics is concerned, we've put the model together and we're ready to look at the cosmological implications of this flavon. I'd like to stop here for a few seconds to see if anybody's got a question. Is everything clear? But also don't worry if you kind of zoned out halfway through. The only thing you need to remember is that there is an absolute lower bound on the VEV of the flavon from CLFE processes.
Yes, I have a question, Venus. Maybe a silly question, but in this last diagram where you have mu to E gamma, this photon is coupling to the eta particle.
So the reason people usually kind of draw it like this is because if eta is neutral, which it is in this case, yeah, the photon doesn't couple to this guy. So the photon could be radiated off of here, or off of this leg, or off of this leg, because these are charged leptons, right?
Okay.
If this was a charged particle, you had a different process, then the photon could couple to here as well. But kind of when you kind of write the amplitude and then calculate the cross-section of this process, there is a bit of a cancellation between the different versions of the process, the ones where the photon is radiating off of different leptonic legs. But basically, yeah, you obviously have to take into account all of those processes. But because they don't want to draw 3 different diagrams, they just have it radiating off out of nowhere. But the assumption is that, yes, you have taken into account all the possible topologies of this process.
Okay. Anybody else has questions?
Sorry, that was a question for me, or?
No. I mean, from the audience, you have questions? If not, you can go ahead, Venus.
Okay, good. So, done with particle physics, let's talk a little bit about dark matter. So, we know dark matter exists, we just don't know what it is. And we have very good reasons for believing that it does exist. the term dark matter was coined by Fritz Zwicky in the 30s, when he basically looked at galaxy clusters, and using the virial theorem, he kind of looked at the kinetic energy and the potential energy in the system, seeing how this galaxy cluster is rotating, and basically the visible mass that was within the galaxy, that what the kind of visible stuff could account for, wasn't large enough. With the rotation that the galaxy had, it should have kind of fallen apart, but it wouldn't, kind of claiming that there is some other mass in there that we don't see, but has gravity and holds this galaxy cluster together. And because we cannot see it, we call it dark matter. That obviously isn't the only reason we believe that dark matter exists. And this list isn't exhaustive. I just kind of mentioned the ones that are fun to me. So another kind of unavoidable evidence for dark matter was found in the 60s, where they looked at not necessarily at the galaxy cluster, but even as a galaxy, measuring the kind of rotation of the stars closer to the center of the galaxy or far away from the center of the galaxy. And what you would expect would be that the further out you go, as kind of the masses of the stars, the visible stars, are kind of accumulated in the center, you would expect a smaller rotational velocity as you went to the edges of the galaxy. But actually what was observed was that the velocity went up and kind of just stayed constant, as if you're not looking at, let's say, 3 separate things running, but as if you're looking at a kind of solid disk, that wherever you look on the disk, you see the velocity, the rotational velocity of each point is the same. So that also kind of gave an indication of what we actually see, or what the visible matter can account for isn't all there is in the galaxy. Another evidence for the existence of dark matter is the patterns of the CMB, which are basically a result of a fight between the outward push of the photons and the inward pull of gravity. So normal matter could be pushed away by the photons, but also feels the gravity. So it kind of creates this interesting pattern in the CMB. But dark matter feels the pull of the gravity, so could go towards the more dense regions, but it does not feel it doesn't interact with the photons, so it doesn't feel the outward push of the photons. So it kind of definitely has an effect on the pattern. And the Planck experiment has actually got a very cool simulator. You could just go to their website and produce whatever kind of universe that you want, move around the values of ordinary matter, dark energy in your universe to see what the CMB of that universe would look like, and you get to compare it with the CMB from our universe. And you won't be able to get a CMB that is vaguely similar to our universe's CMB unless you account for a good 25% of dark matter. Another kind of very good, let's say, no, you can't call it a smoking gun, but very good evidence for the existence of dark matter was the bullet cluster merger, that the two galaxies kind of collided with each other. And if they were just made of ordinary matter, you would expect as the result of the collision, most of the matter to stay kind of near the center of the collision. Whereas what the simulations showed and what they observed from both X-ray experiments and gravitational lensing observations, what they saw was that, sure, the visible matter kind of stayed around of the center of the collision, but the dark matter components of each galaxy kind of went through each other as if they have kind of the sliding through. They have no interaction with the visible matter. So yeah, the kind of results that came out had the red bits that are kind of representing the ordinary matter, which are accumulated in the center of the collision, whereas the blue bits, which are representing dark matter, kind of have gone to the outer parts of the collision center. We also have these kind of sky surveys, which give you a kind of, well, simulations and observations that basically tell you that at a large scale, the galaxies and galaxy clusters kind of form these filaments and, you know, dense regions and void regions. And the only way we could get our simulations to agree with observations is that if we account for dark matter. So as I said, this is not an exhaustive list, but basically we have a lot of evidence which confirms that we do have dark matter. But what it is, nobody knows. We only have kind of rough ideas. So one of the most kind of studied or well-motivated dark matter scenarios are the kind of WIMP scenario, the weakly interacting massive particles, which are assumed to be in kind of thermal equilibrium with the standard model bath in the early universe. And as the universe kind of cools down, as the universe expands and cools down, your the interactions between dark matter and the standard model particles that keep the dark matter in thermal equilibrium with the standard model bath kind of fall out of equilibrium, and dark matter basically freezes out. So what you have to do is that you have to look at the rate of this interaction and compare it with the Hubble rate, which tells you at whichever point the Hubble rate is faster than the interaction rate, then basically that means that the universe is expanding faster than two dark matter particles could find each other and annihilate. And basically what happens is that your dark matter freezes out, the expression is, and you are left with a certain relic abundance. So in the normal kind of freeze out scenario, if you have, the stronger your interaction is with the standard model particles, the longer you stay in thermal equilibrium, right? So if you kind of fall out of equilibrium with the standard model bath earlier, there would be more of you left than if you stayed in thermal equilibrium with the standard model for longer. I really like to use the analogy of a train that is kind of heading for a cliff. And the sooner you jump out of, let's say, you and your buddies, the dark matter particles, the sooner they jump out of the train, there's more of them left. Whereas if they stay on the train and kind of have a big fight with the standard model particles, more of them are going to be dead. And if you don't kind of jump out of the train or lose your interaction with the standard model particles, you'll be completely doomed. So that's for a stable dark matter. As we go further, we'll discuss a dark matter that is also decaying. Sure, it is very light and it's got a kind of very long lifetime. It decays very, very slowly. Nonetheless, it does decay. So the story is a little bit more complicated, than just a stable WIMP scenario. But what is kind of good to remember is that what we're saying here is that if your interaction is stronger with the standard model, you will stay in equilibrium with the standard model particles for longer. And remember that the interaction rate is inversely proportional to the VIV of the flavon. So if you have a large flavon VIV, that means your interaction rate is actually smaller, meaning that you will fall out of thermal equilibrium earlier. So for example, you will be in thermal equilibrium through processes with heavy standard model particles, with taus, with mu's. But if your wave of the flavor isn't very large, meaning that your interaction rate is high, you could stay with the standard model particles up to late stages. So even electrons could be kind of playing a role in the production of dark matter. So that's the normal freeze-out mechanism that we all know and love. But I'm sure you've heard of the freeze-in mechanism, which is a kind of alternative scenario that could also lead to production of dark matter. For the freeze-in mechanism, usually they assume that in the beginning of the universe, the abundance of dark matter was almost zero. So this is quite different from the freeze-out mechanism, where you assume that in the beginning, your dark matter was in thermal equilibrium with the standard model particle, and you had an original or initial abundance. In the freeze-in case, which are kind of describing feebly interacting massive particles, or FIMPs, you assume no initial density or abundance of dark matter, but kind of as time goes on, more and more of your dark matter particles are produced, until you reach a point where the Hubble rate is larger than the interaction rate that produces your dark matter, and you won't be able to produce more, and you kind of freeze in the amount of dark matter that you have. So in this case, then increasing, so by lambda here, they mean the kind of coupling of the interaction. Here, if you increase the coupling, you're basically producing more of this stuff. So that would be reducing the wave of the flavor. But let me not confuse you any further, and kind of go further and see if we could now put these two bits together. So from the particle physics bit, we know that we've got a scenario that perfectly explains the charge lepton mass hierarchy, and it kind of provides us with a pseudo Goldstone particle, which is very light. It is decaying, but we want to see if it can kind of contribute to the observed dark matter relic density. So before I go to the next bit, are there any questions? Good. Okay. I hope that means that everything's clear. Okay. So when we actually started with this project, we were quite happy, thinking, woohoo, we've kind of connected these two problems together. And of course, how difficult would it be to take this flavon to be a dark matter candidate? And it turns out we were very wrong. So the first thing you want to worry about with a decaying dark matter is its lifetime. Is it going to be around long enough that it hasn't decayed all the way? So again, as I mentioned, if this particle is heavy enough, it could decay to, let's say, the lightest pair of charged leptons, 2 electrons. But if we assume that this channel is kinematically forbidden, by assuming that the mass of the eta is less than twice the mass of the electrons, then kinematically, eta cannot decay to 2 electrons, but it could still decay to 2 photons through a loop of charged leptons. So one has to calculate the amplitude of this process, which you see will depend on the mass of eta and these copper tilde couplings, which, remember, were inversely proportional to the wave of the flavor. So this is the dominant process that through which dark matter decays. Let's see if we could get this dark matter to be long-lived enough to kind of account for dark matter. So you would want this tau eta, or the lifetime of this particle, to be larger than the age of the universe, which is around 10 to 17 seconds, which is, as you see, proportional to the mass of eta. But yeah, don't be fooled thinking this is just a linear proportionality, because remember that this matrix squared also depends on the mass of the dark matter and the wave of the flavor. But basically, for a quick kind of check to see, can this particle be long-lived enough or not, you see that depending on the mass of this particle, let's say for a 10 keV eta, the wave of the flavon would have to be around 10 to 6 GeV, which is still quite a kind of hot dark matter, let's say. For an eta of 1 MeV, the wave of the flavon would have to be 10 to 13 GeV, which is quite close to the Planck scale. And then, as I mentioned before, you're again struggling to kind of justify the scales in your model. And originally we started with, there's no scale in the fermion masses. Here's what our beautiful theory does for you. So it's kind of a little bit funny to then say, oh, by the way, there's another scale. There's the wave of the flavon at the 10 to 13 GeV for no good reason. So kind of having run into a little bit of trouble trying to justify our dark matter, what we did was that we kind of checked to see, so with kind of smaller waves or more, let's say, down to earth waves, is there any bound on the abundance of this particle? Can it be all of dark matter or not? Because already you could see when you go to very light values, your dark matter particle is getting to the areas of hot dark matter. If it's a relativistic particle, then you have to worry about constraints from small scale structure. So you do then have bounds on the abundance. So we thought, okay, that's the only bound we need to worry about. But we came across a couple of cosmological papers that showed us, actually, you were wrong. There are much more stringent bounds that you need to worry about. But before I get to that sad story, let me tell you kind of, you have to, if you want to see what kind of bounds you have on the abundance of your particle, you also have to look at the production processes. So we basically looked at all the interactions that eta had, trying to see at different waves which processes would be the dominant ones that would be producing eta. So again, remember, as the wave of the flavon grows, the interaction, so the couplings which are inversely proportional to the wave of the flavon, are going to be weaker and weaker. Kappa tilde is smaller for large waves. So if kappa tilde is smaller, it means that your dark matter would run or fall out of thermal equilibrium with the standard model path, meaning that it is not around until, let's say, processes with electrons involved would play a role. So at very high waves, you see that it is mainly these processes that are the dominant production mechanisms for your eta. And basically what we've done here is that we've done this kind of assumption that when your Hubble rate is exactly equal to your interaction rate is when you run out of or fall out of thermal equilibrium. And then that specific temperature where this happens is called the freeze-out temperature, right? The standard kind of framework that the freeze-out mechanism predicts, where the freeze-out time is basically almost the mass of the heaviest particle in the process. So because we're kind of doing the analysis in this way, that means that you kind of have a production that is very much step-like, because we're using the kind of rugged assumption that any time later or earlier than this, there's a different process that is the dominant process. So, for example, here you see that for a certain range of the VIVs, it's the WW process or WWZZ fusion that produces your eta particle. Whereas if you had, let's say, a different window of the VIV of the flavon, it would be a different process that is the dominant production process. And if you have a different VIV, again, so this is not a, it is because of the assumption that we're making, the freeze-out assumption, that the production comes out as this step-like function. Obviously, if one wants to do a proper kind of numerical check, then one would have to actually numerically solve the Boltzmann equation to see what exactly is happening at the point where we kind of approximate the model. But for the purposes of this work, this approximation is perfectly fine. But basically, that's what describes this step-like behavior, that at low VIVs, when the coupling with the leptons are larger, you stay in equilibrium, let's say, with the standard model particles all the way up to where the electrons are still present for you to kind of interact with. And also remember that the abundance of dark matter also depends on the mass of the dark matter, because the heavier the dark matter is, the more it decays into photons, right? So if I go for a kind of, am I saying it correctly? Actually, maybe let me bring you back to this equation. Yeah. So it's not just the mass of eta that you see explicitly here. There's also the mass to the power of 4, which is here, which basically shows that the lifetime of this particle is inversely proportional to the mass Q, right? So if I change the mass of my dark matter, the abundance of my dark matter changes as well. Not because it due to the fact that this is a decaying dark matter, right? So what is really kind of interesting here is that below this point, when your VIV of the flavon is smaller than this value, there's no cosmological reason for your kind of data point stopping here. The reason is purely particle physics related. Remember that I said from the CLFV processes, the mu to E gamma branching ratio bounds that you have from experimental evidence, no matter what the mass of your eta is, as long as it's much lighter than the muon, the VIV of the flavon has to be above 14 TeV or so. So this is actually what the lower bound is. This is purely particle physics related. As you go to higher VIVs, the production process changes. And then what happens over here is that at kind of values above 10 to 8 GeV for the VIV of the flavon, the VIV is so large that the interactions with the standard model are so weak that your dark matter particle never actually comes into thermal equilibrium with the standard model bath. So you're not actually producing your dark matter through a freeze-out process. The interactions are way too weak, but you could produce it through a freeze-in mechanism. So that's what I actually show here. Having taken eta to have the 1 MeV kind of exemplary mass, you see that we have the same story as before. The very, very small VIVs give you a large charge lepton flavor violating contribution, which means that your VIV is not allowed to be smaller than this value. Then as you go for different values of the VIV, which by the way affect the lifetime of your particle as well, there's a different process that is producing your dark matter. But as you go above 10 to 8 or so GeV, the interactions with the standard model are so weak that your dark matter doesn't come into a thermal equilibrium with the standard model bath, and you're basically producing it through a freeze-in mechanism. So then this jump obviously is not a physical thing. It is due to the assumption that we think, okay, from this point onwards, ether doesn't thermalize with the standard model bath anymore. And it's a different process that is kind of in charge of producing ether. If you want to do a very realistic kind of plot, one would have to numerically solve the Boltzmann equation to see what exactly happens here. So yeah, this is not a physical discontinuity, it's just due to the assumption that we are making. So yeah, and as I said, for like one given mass, you could basically then see what is the abundance of your ether, which we have kind of normalized by the abundance of dark matter today, because all the experimental kind of or observational plots that you get that are relevant to our work basically do this. So they always normalize the abundance of your decaying particle, let's say, by the abundance of dark matter today, which means that if you're on this red line, that's when you are kind of contributing to 100% of dark matter abundance, which you can see for the example that I've chosen. Our abundance is well below the 100% dark matter relic density, is like 10 to minus 4. So it's very, very small. So yeah, as I told you before, while we were happily thinking that we only need to make sure that our decaying dark matter is long-lived enough to be able to produce or kind of hit two birds with one stone, and use the Frogincent mechanism to also explain the relic density of dark matter. But we were wrong. So this is a paper which is quite kind of astrophysical or cosmological. So I'm not sure, I don't exactly understand what these things are, but basically what the plot says is that if you have the abundance of your decaying particle that specifically decays to, let's say, photons, so normalized by the abundance of dark matter today, so this would be 100% relic density. The abundance is quite constrained at so early times in the universe. At the very, very beginning of the universe, if your particle is only that long-lived, it decays so rapidly that none of it is left for any cosmological bound to apply on. If your particle is a little bit more long-lived and is decaying to photons, injecting energy into the standard model path, you are quite constrained by Big Bang nucleosynthesis. So basically, what this pink region said.
Venus,
Yep.
What is the quantity in the y-axis?
In the y-axis, this is the abundance of your decaying particle, in our case eta, divided by the abundance of dark matter observed today.
Okay, sure.
Yeah. So this line, 10 to 0, so 1, would be the abundance of dark matter today. So if your particle was very, very short-lived, you'd be allowed to have as much of it as you want. But as your particle is a little bit more long-lived, but this is still quite a short life, right? I mean, this is 3 minutes or so. But your particle is decaying into 2 photons, right? So it's injecting energy into the bath. And at early times, by the Big Bang nucleosynthesis data, your abundance is constrained to be below this value. So, for example, if the lifetime of your particle is around 10 to 8 seconds or so, you're only allowed to have 10 to minus 5 times the abundance of dark matter today of it. So for a very short-lived particle, there are quite constraining limits on its abundance. If you go to a little bit later times, it's the CMB patterns that are putting a very, very tight constraint on the abundance of your particle. So here, basically, from the age of the universe is around 10 to 17 seconds or so, right? So if your particle was long-lived enough with a lifetime as the age of the universe today, so again, a particle is decaying to photons, its abundance would have to be below 10 to minus 9 of the dark matter abundance. So clearly, you're decaying to photons. Energetic photons are kind of being injected into the universe, and you would see they would definitely have an effect on the CMB patterns, right? You are allowed to have such a particle, but only if the abundance is so low that it wouldn't matter. So as you can see, the bound on the CMB goes all the way to 10 to 24 seconds or so, which is way in the future. But still, that basically means that the abundance of your particle, even if it's very, very long-lived, still is quite constrained. We didn't really realize that the CMB constraints would be so strong. But yeah, there it goes. It shows you that if you want to have a decaying dark matter, you would really have to worry about astrophysical bounds. So what we did was that kind of translated this or digitized this plot into our kind of plot form. So I've done basically, this is exactly the same thing. The BBN bit I've showed by a green kind of colored region, and the CMB ruled out bits are the blue regions. So what we did here was that, again, remember that for different masses, you have different abundances, and for different kind of windows of the VIV, you have different production mechanisms. But the kind of the mass windows that are interesting are basically what we've tried to kind of show here. So this orange line, it corresponds to an eta of 14 MeV, so milli electron volt. What basically this is that for a dark matter of such mass, which is quite light, meaning that it doesn't decay too much. There are so I mean, first of all, the lifetime of this particle is longer than the age of the universe, right? The age of the universe today is 10 to 17 seconds. So you don't see the explicit dependence on the wave of the flavon in this plot, but by kind of looking at the step-like function, you know what these regions or what flavon wave window this region is. Let me remind you that any vivs or any, let's say, lifetimes, which do translate to the wave of the flavon, smaller than this value are ruled out by the non-observation of CLFP processes, right? So any VEV less than this value is not, your model isn't kind of constrained by any cosmological data. And if you go for a lifetime larger than this, or a flavon VEV larger than this, your particle won't be thermalizing anymore. It will be produced through a freeze-in process, and its abundance could be whatever. One thing that you need to worry about is that if this is now a hot relic, from the small scale structure, you have bounds on the abundance of such a hot relic, which is kind of about 1% of the observed relic density. So as long as you were below, let's say, 1/100th of the dark matter abundance, your model is fine. If you go to an eta mass which is a little bit heavier, that means the lifetime of this particle is shorter, which means that there would be cosmological data that would constrain your model. So any value of eta mass between these two would be exposed to some cosmological bound, but it would also have regions which are not constrained by any cosmological data. This 3 eV is the limit where the freeze-out production of your dark matter is completely ruled out. Okay, so if you're moving in between 14 milli-electron volt to 3 electron volt, there are regions of the parameter space where the freeze-out production of eta is perfectly fine. But any value heavier than 3 electron volt, the freeze-out production of your eta, let's say dark matter, is completely ruled out. The abundance would be so much that you would be injecting so many energetic photons into the CMB that you'd be completely ruled out. So that's the freeze-out production. From the freeze-in production of the model, when your VEV is larger, meaning that your interaction strength is smaller, you could kind of avoid the CMB bounds and produce a relatively good amount of your dark matter. So as you see, this line just carries on going down as the VEV of the flavon goes up. The interaction rate goes down and the lifetime of the particle goes up. But there are certain regions of the VEV or lifetimes that are ruled out by the CMB. And again, 3 electron volt is still a hot relic. So you do have to worry about the abundance not being above, let's say, 0.101 of, 0.01 of the observed relic density. Then any value between 3 electron volts and 1 mega electron volt, you could have, so freeze out production of the model is completely just out of the question, but you could produce, or you could have some amount of it left over, having produced it through the freeze-in mechanism. When you get to 1 mega electron volt mass, then you're basically so short-lived that the particle just completely dies out before any of it is left behind to have any cosmological constraint apply to it. You could still produce the model through freeze-in, and this line should theoretically carry on. I just didn't allow for VEVs above whatever 16 GeV, 10 to 16 GeV or so, which would kind of be too large. But through freeze-in, you could still produce your dark matter candidate, provided your abundance is very, very small. I mean, 10 to minus 6, 10 to minus 7 times the abundance of dark matter that you observe today. And yeah, its lifetime would be around the age of the universe now. If you go to any mass that's above this, then basically your eta could decay to 2 electrons at tree level, and its lifetime is just it's so short-lived that it doesn't make sense to even try to apply cosmological bounds to it. So basically, that's what this analysis showed us, that very much dependent on your interaction rate and the mass of your particle, you could produce it, a certain amount of it, with different mechanisms. But to kind of, for eta to be exactly, to contribute to 100% of the electron density, it is quite difficult thing to do, because either your particle would be too short-lived, or it would be long-lived enough, but so light that it would be a hot relic and would be bound from different kind of cosmological data. So what we did was that kind of having taken, so as you can see, we've taken like points to kind of fill up the whole region. That's why you see these jagged sharp tooths here. But if you kind of run a numerical simulation for every single point, you see that this would be a smooth line. But basically what it says is that there is a correspondence between the mass of the flavon and the wave of the flavon, where in the very low mass regions and very small waves, it's the particle physics data, the charge lepton flavor violating data, that rules out your model. Whereas when you go to kind of heavier eta particles and larger waves, then your model is constrained from basically CMB, BBN, small scale structure, and the heavier the mass of your eta is, the larger your wave of the flavon has to be. Otherwise, yeah, your model is basically ruled out. Yeah, so that's all I had to say. I'm just gonna flash the summary plot. I've gone quite past my time limit as well, but thank you for staying with me throughout, and please let me know if you have any questions.
Thank you, Venus, for this nice presentation. So, guys, do you have any questions? Again, feel free to text it in the chat or open your microphone.
Hey, Venus.
Yeah.
Does it work? Yeah. Okay.
Yes, yeah,
So when you were talking in general about the mechanism and assigning charges, you chose certain charge assignments, and then you were talking about the dark matter behaving this and that. Did you does that depend on whatever charges have you chosen in?
Yes. So yeah. So the reason we chose the charges that we chose was that we kind of we wanted to increase the lifetime of the particle as much as possible. So actually, the first thing we calculated was this process, knowing that, okay, we don't want it to decay to 2 electrons. So we put this process together, and basically wanting the lifetime to be quite large, we assigned the charges in such a way that the leading contribution canceled out. So this is actually the next to leading contribution. The charges that we've put together, as you saw here, actually kills out the leading contribution. So that was kind of, this isn't the worst case scenario. Of course, you could still move around the charges and change your order 1 coefficients as well, and have kind of a very long-lived particle. But this was one of the choices that kind of gave us the best option. But if you kind of willy-nilly choose a set of charges, then your lifetime will be a little bit shorter.
Yeah, because, I mean, from what I understood, they are completely arbitrary, right? I mean, there is no I mean, apart from having the symmetry, and that is like the only constraint that you have. Everything else you have to sort of choose to get sort of the right masses, and then if you plug that dark matter part into it, then it has to be sort of, you just exclude certain things because they, I don't know, they decay too quickly or have to do something else. But there isn't any fundamental reason again for
absolutely not.
They can be whatever.
Yeah, so in a sense, this Frogincent mechanism is a good mechanism because you could explain a lot of things with it. I mean, as I said, the first time we kind of thought of using this mechanism was when we were trying to explain the Higgs to mu tau signal, which would have meant you would want this component to be large enough, right? So the charges that we assigned were in such a way that the epsilon power here was smaller. So this was also like epsilon to the power of 2 because we wanted to have a large mu tau mixing. And yeah, you've got so much freedom. You could choose the value of your epsilon, you could choose your charges, and you still have these order 1 coefficients. It's not, very straightforward to get exactly the correct kind of Yukawa couplings for the mu e tau, but it is doable. You see that you have a bit of freedom, and if you don't want to do anything crazy like explaining a mu tau, large mu tau mixing, it's not too difficult. But whenever you ask Frogincent or Nielsen to kind of justify the charge assignment, they would go, in the standard model, the electric charge is just random. What is minus 2/3? Do you have an explanation for minus 2/3 or hypercharge? Do you have an explanation for 1/6? No. Therefore, we have no explanation for the charges 3, 2, 1 or whatever.
It looks to me a bit like pushing the problem to another area. I mean, then why do you have a problem with Yukawa couplings being so like the orders of magnitude different? I mean, you truly do not explain anything. I mean, it's this, as you said, I think it is this being the generational thing, how natural certain things are, and what do you consider to be a natural choice, and arbitrary, you don't consider that to be a natural choice.
Exactly. I mean, to me, I'm perfectly fine with the masses being whatever they are. To me, 2 orders of magnitude mass difference is very much the same as saying, there's a difference between the charges. But the kind of the defensive way of answering it would be, that's like a couple of orders of magnitude, whereas these are all order 1 coefficients. But it really depends on your taste, I guess.
Okay, I have a question from Clarissa. I will read it. Could you please comment a little bit more about the impact on the structure formation? This little mass can be ruled out?
So let me see if I can go any further. So if I may, I'd like to refer you to this paper, which is kind of, it's like as if it's written in a different language. I'm not an astrophysicist, and I struggled a bit to understand it. But basically, so the CMB bit is, as we're talking about the pattern of the CMB, that is kind of a fight between the outward push of the photons and the inward pull of matter and dark matter, which kind of doesn't interact with the photons, but feels the gravity of the matter. So if you have a dark matter particle or a particle that is quite abundant and is decaying to photons, then you're producing a lot of energetic photons, right? So it would have an effect on the pattern of your CMB. And that's basically what this plot is saying, is that well, depending on the age of this particle, which is translating into how fast it decays into photons, right? The abundance of your particle is quite constrained. It could be as, let's say, short-lived or the same age as the universe, but that means that you would be injecting a certain amount of energy into the pattern of the CMB. And if this particle was very abundant, it would have changed the CMB pattern. If your particle was short, there was some of this particle that was producing photons, but there was so little of it. Let's say, I mean, this is a ridiculously small amount, 10 to minus 18 times the abundance of observed dark matter today. That's a very, very, very small abundance, meaning that the injected energy wouldn't have been so much. So yeah, and when you go, the reason this line then goes up as the lifetime of your particle goes up, it means that this also translates into the particle doesn't decay into photons. The rate of that process isn't very large. So basically, you're not injecting too many photons. So yeah, so that's the bound that you get from the CMB. From the BBN, basically, again, you've got a particle that is kind of that is shooting what do you call electromagnetic energy, or this energetic photons into the standard model path, and we have a very kind of a good understanding of what happened during the Big Bang nucleosynthesis. We know the abundance of the chemical elements, and our theory agrees with observation very well. So if you have this new particle that is kind of coming in, injecting energy into the bath, it will mess up. It will definitely have some observational evidence, which again the BBN data constrains quite a lot. Usually with the BBN, you also get a bound on the number of degrees of freedom that you could introduce to the model, but this is a scalar. Yeah, so I think the amount of the error that you have on the degrees of freedom that you're still allowed to introduce into the BBN is like one point something, and a scalar, yeah, 1 degree of freedom, that's fine, but it's the fact that it's decaying into standard model particles that's causing the trouble.
Okay.
Yeah, but as you can see, that also depends on the lifetime of the particle, right? If the particle was more long-lived or was injecting less energy into the system, that would have been okay. But yeah, large amount of it is certainly not allowed. Does that make sense?
Yeah. Do you have more questions? I have not actually a question, a comment.
Yep.
This eta particle resembles a lot an axion. The symmetry is not the P-shaped symmetry, but it is a pseudo-Goldstone boson, and
yeah,
in that axion-like scenario, they managed to reproduce the full relic abundance, but I think that the mechanism of generation of this relic abundance is different. That's
yeah. So the setup is very much like an axion-like particle, but yeah, this is kind of leptophilic flavon. It has nothing to do with the quarks. With exactly, yeah. So with the QCD axion, then you have these couplings to the quarks and whatever. So there are other constraints. I don't know off the top of my head if they haven't. Let's see. So I think with the QCD axion, the problem is the fact that it has to be quite light, and it will be a hot relic. So you would be quite constrained on its abundance. Let's say if it wasn't a decaying particle, if it was perfectly stable. But I know also that there are other kind of production mechanisms for axion. For example, this misalignment mechanism, where you don't, you're not thermalizing, you're not producing your dark matter through freeze in or freeze out or any of that. It's just the resonance oscillation of the axion field that kind of produces it. In that case, you don't get the abundance bound on the hot relic anymore, and you could kind of have a larger abundance of it. But I don't know what the current status is on that. I don't even, people must have looked into it, but I don't really know. I should look it up.
Yeah, it's a completely different scenario.
Yeah.
So, okay, more questions? If not, I think we can stop here. Let me thank you again, Venus. Thank you a lot for
Thank you very much.
being with us today. Thank you guys from the audience. So we see you next meeting. And bye guys.